Good evening, everyone. Welcome to this month's virtual Didsbury Sidebar. It's great to see you all. Tonight we have Dr. Sarah Bergin, who is going to talk to us about science and the fire service. She's a scientific consultant and amongst other clients is the fire service. So she's going to enlighten us all about that. Thank you very much, Sarah.
Okay. As Sarah said, it feels weird talking in third person. I do consultancy a lot around chemical and hazard management. So one of the kind of roles that we have in this is to offer scientific support to the fire service. So one thing I didn't quite appreciate, I guess, is just actually how much science the fire service find themselves involved with when it comes to the instance. So I'm Irish, so if I do start to talk too fast, somebody put a hand up or say something to slow down. But anyway, so hopefully everyone can see the screen. These pictures on the right are pictures from incidents that we attended. Just to give an outline about the presentation. So I've got a couple of slides on the fire service structure and incident response. So just to give you a bit of an idea as to how hazardous materials response kind of fits into the fire service structure. Classifying hazards as well. So as scientists, quite a few of you might be familiar with the globally harmonized system. So the system for like labeling and packaging chemicals. And it's often something that the fire service themselves are trying to get to the point where they can classify a hazard. Because ultimately you're either the chemical will have reacted and disappeared and there's nothing to clean up, or there is something to clean up and it needs to go to the right place. And then there are a couple of incidents that I'm going to talk about, so and some of the science that is related to them. So some of the kind of underlying fundamental properties that the fire service are considering. So just what the fire service, the Fire and Rescue Services Act. So these are the key responsibilities for the fire service. So we always think their kind of role is to extinguish fires, but within that they are trying to protect life and property as far as possible. But then in the kind of next 2 points after that, rescuing and protecting people in the event of a road traffic collision and in the event of other emergencies. So the police will head out to crimes, ambulance will head out to an injury, and the fire service go out to everything. So they do find themselves at quite bizarre kind of situations. So within that, you've got the kind of main crew members. So the first responders to an incident will generally be a pump, so a fire appliance with the crew turning out from the fire station. Kind of commanding that structure is someone appointed as the incident commander. And this is going to be the main person that is making all the tactical decisions when it comes to responding to an incident. He or she will have support from a command support. So that isn't just one person. It could be multiple people depending on how big the incident is. You've got sector commander. So if it was something that is getting to the point where actually there are 8, 15, 40 pumps with a lot of crews turning out, we'll have sector commanders. So the incident commander, the kind of main person making the decision, no matter how many people turn out to an incident, he will never be talking, or she will never be talking to more than 4 people at a time. So it's a very kind of rigid kind of operational structure, which is necessary in an emergency situation. You do have these other kind of bolt-on roles. So you've possibly seen what the fire service called the Teletubby suits, which is the gas-tight suits. You've possibly seen them when it was Salisbury, and these are the kind of highest level of protection if you're dealing with a really toxic environment. USAR, so that's urban search and rescue. So that could be building collapses, post-earthquakes, etc. And then you've got tactical advisors. So that is kind of the one that we're potentially interested in. So these can be liaison officers, so they could be liaising with the police or media if it's a sensitive situation, or the one that I'm particularly interested in is the hazardous materials advisor. So these are the guys that will go out if there are chemicals involved, and the incident commander needs a bit of additional specialist knowledge. So the name does change. So there's the HMEPO, I think is now the name, but the HMA, the Hazardous Materials Advisor, was the original name. One thing with the fire service is they have a lot of abbreviations. So I've just about learned them all, but at the start I was thinking, what are you talking about? But anyway, so Hazardous Materials Advisor, so their role is to gather, filter, and interpret the technical information. So if an incident commander or the initial kind of memo that's going out is suggesting there's chemicals, the hazardous materials officer could be notified fairly early on. These guys and girls are essentially station managers, watch managers who have this additional bolt-on role. So they're not kind of standing by waiting for a call about a chemical. They're actually doing their day job as a station manager or watch manager. Some of the more rural fire services, they might also be the animal welfare officer. So I've had some officers say to me, oh, I was pulling a cow out of a ditch the other day. So their kind of role does change depending on how their structure is in their own fire service. But essentially they're there to assess the risks that are posed. So of course, the incident commander is interested in protecting the public and life, but also need to think about the crews themselves and how they're going to approach it and their safety. So it's all of those kind of risks. And that is essentially what the hazardous materials officer is doing a risk assessment in terms of the hazards that are there and then providing advice. So this is something I just pulled out of their response manual, just around to give an idea of what they're typically doing when it comes to a hazardous materials incident. So phase 1 is mobilizing and en route. So that will be the first call will come in through fire control. So the first thing that they will do, regardless of chemical or not incident, is to get a weather report. So what is the wind speed? What direction? If we're going to have smoke plumes, if we're going to have chemicals disappearing, what direction are they going and how far are they likely to go? There's the emergency response guidebook, which is quite a generic advice kind of guidebook related to the United Nations numbers or hazard classifications. And that's to give an idea of the initial cordons. So as I said, the pumps, the guys on the trucks will be the first ones there. A hazardous materials officer won't be there within the 8 minutes that the pumps are trying to get there. So they will already have set up a kind of initial cordon themselves based on these kind of, okay, it's this chemical, it's daytime, so we set a 50-meter cordon. So that is kind of what they're doing in their initial phases. You've then got phase 2. That picture on the left is from Saddleworth Moor fires. It was, I didn't take that one. I couldn't get that high, but essentially that was what Saddleworth looked like a couple of days into that incident. The one on the right then is thorium oxide. So it's a radioactive powder. So arriving and gathering information. So that is looking at, well, who's at risk? So are we in a workplace? Have we got vulnerable individuals? Is it children? Is it elderly who might be more susceptible, not the healthiest? In this case, obviously with Saddleworth, that was a much larger scale. So how big an evacuation do we need to be considering and how quickly? Quantities and hazards. So of course, looking at that little vial, it's not a massive quantity. However, if you decide to eat a radioactive powder, that's quite a bad hazard. So it's just considering from the initial information that you have, what you're going to do next. Once you kind of have that information, and as you gather more, you start getting into this cyclical process. So phase 3, 4, and 5, where you're planning the response. And that again is coming down to looking at information that you have. So some of you possibly know the workplace exposure limits if you work with chemicals, the EH40 guidance. And this is related to, it's designed for people who are working a 9 to 5 for 40 years. And if they're going to be exposed to chemicals, what is the acceptable level? Of course, you forget, it is an emergency response. However, the fire service themselves are workers. So you do need to kind of consider their workplace exposure as well. There's a little table on the right there, the acute exposure guideline levels, which the fire service abbreviate to EAGLES. So if they're talking about EAGLES, this is what they're talking about. And these are emergency guidelines. So obviously, if you're in an emergency situation, you're going to expect to potentially be exposed to a higher concentration of that chemical than if it was your place of work. So there is an allowance for that. These levels, when you're talking about EAGLES, are unfortunately, they're the most detailed information, and it's because a lot of mice and rabbits and other animals have been tested on. So there's about 70 or 80 chemicals that have this level of kind of information around exposure levels. So these are kind of the most detailed ones, but there are other limits that the fire service will work to. And this is kind of, in terms of their tactical strategy, looking at, is there a savable life here? So if you're into EAGLE 3, this is essentially, it is expected that someone will have died if they are exposed to these levels. So in terms of their tactical response, they'll be looking at trying to rescue EAGLE 2 people who can potentially be saved. So all of that kind of happens in a cyclical process, but the phase 6 then is closing the incident. So as I said, it could happen that the reaction has happened, something has gone to flash over and everything's disappeared. Fine, it's just a cleanup in that way. Or you might have chemicals that you have to deal with. And the fire service will try to work to hazard classification. So if you're handing back to the local authority, it's helpful to say this is a flammable liquid, this is a corrosive substance, so that they can kind of inform on how they're going to actually deal with that. So that brings me on to hazard classification. By the way, if there's questions popping up, we can stop every now and then if people want to ask questions. Pace is all right, is it, Sarah? Yeah, okay.
Yep, sounding good. If you've got questions and you don't want to ask them out loud, then feel free to just pop them into the chat window, and we can ask on your behalf.
Okay. So as I said, hazard classification. So if some of you work with chemicals, and even if you don't, you've possibly seen this on some of the bottles of cleaning agents that you've bought or anything like that. This is the globally harmonized system of classification. So this kind of came about because we are now, transporting chemicals all over the world and globally. It was felt that there needs to be a kind of recognizable system of categorizing hazard, so that no matter where it goes in the country, you understand and you have these hazard classifications to work with. So again, this is for labeling and packaging. So you'll see it on boxes, on bottles, etc. Just to kind of go into more detail, as an example, here's methanol. So in this case, methanol has 3 hazard diamonds on it. And generally, when you're looking at labeling, the most hazardous, the greatest hazard in those will be the top diamond. So in this case, flammability and toxicity are kind of the more hazardous of the 3 hazard classifications. The word danger as well, so if it says danger, that is thought to be more dangerous than something that said warning. So there's all these kind of classifications that you can get just by looking at the bottle. This is the one that's possibly a little bit more, the fire service would be using a little bit more, and this is the UN Transport of Dangerous Goods. So it's the Carriage of Dangerous Goods Act, and this does align with the globally harmonized system. And these are the diamonds that you'll possibly be seen on tankers on the road. So these are specifically for classification. So you could have your GHS, your other pictograms on your bottles, but on the outside of the tanker, you'll potentially have these diamonds. There's 9 hazard classifications. Miscellaneous is a great one because it could be anything. It could be asbestos, could be, I don't know, milk if there was enough of it. So, but yeah, essentially hazard transport of dangerous goods. And again, this is because things are being transported all over the world. So we kind of need to be able to understand quickly if something happens that, okay, we're potentially dealing with an explosive, because we can see that hazard classification. But it's just an end there. So as I said, I put this picture up on Facebook about a week ago saying, have you ever driven behind a tanker and thought, what is this all about? So if you see this one, this is unique to, well, I say the UK, but it's in India and Australia as well. So it's called the Emergency Action Code. It's been around in the UK since the 1970s. Its motivation is a bit unfortunate. In the 70s, there was an accident on the motorway in which a tanker had a spill, and a nurse got out on the motorway and ran over to help, and unfortunately ran through the substance, which happened to be sulfuric acid. So she obviously didn't survive that one, but it kind of, highlighted that actually the emergency services need to have some sort of information as quickly as possible. So within the UK, you will only see this on UK roads, or I guess, like I said, if you're in Australia. So the top number and letter combination is information for the fire service. So I've put the kind of HazChem card to the right hand side of that. So in this case, if this tanker had a spill and the fire service saw this, they know, okay, hazard classification, it's a flammable liquid because I can see the diamond. 3YE, it's telling me I need to put foam on it. I need to wear BA and fire kit. Because it's a Y and there's a V beside it, said it can react violently. So they know that. And E is the public safety hazard, so maybe consider evacuation. So just from looking at that, they know this is potential action I could take in the event of this going on fire. You've got a number at the bottom. So the phone number is hopefully the person who sent this out in the first place. You've also got that 4-digit number, and that is the UN number. So there is you can actually download an app. So if anyone, I don't know, as kids, we used to have a fun game of identify the car brand by looking at the logo. So there's actually an app you can download to look at UN numbers. So if you're driving behind a tanker and want to know what 1203 is, which in this case is petrol, you can go and download and look at that. But essentially, those 4 numbers then give the fire service an indication, or the responders an indication as to potentially what they're dealing with. Not all of them are specific, so you sometimes got not otherwise specified. Corrosive material could be as far as that number gives, but it's essentially a classification system for them. So that is, like I said, the UK one. You might also see this one, which is not quite exactly the same. So this is the ADR. So this is the International Transport Regulations. So if you see this, this placard on the road, you will know that that tanker has actually come over from Europe. So the European labeling system, it's fine for it. You don't have to re-tag it if it's going in the UK, but a UK tanker should not go to Europe with this emergency action code. It has to be the International Transport Regulations. So this is a HIN number, so a hazard identification number. So again, that is 1203, so petrol. So again, that's the UN numbers, but the top 2 numbers are essentially related back to the carriage of dangerous goods. So depending on what numbers are there, it will tell you the potential hazard. So 3 is a flammable liquid. So again, in line with the carriage of dangerous goods, but the fact that they've put 2 3s is intensifying it. So if they've doubled the number, it's saying this is very flammable. If something is, for example, flammable and toxic, it would have a 3 and then a 6, or it might have a 6 and a 3, depending on which is the greater hazard. So if it's a higher hazard, if it was chlorine, for example, which is corrosive and toxic and oxidizing, the toxicity would come first. So you can have up to 4 numbers in that top row, but essentially those numbers are telling you what are the hazard classifications. The tankers will always have the pictograms as well, so they will have the hazard diamonds, and like I said, if it has multiple hazards, it will have multiple diamonds. So yeah, just some nugget of knowledge now. If you're driving on the road and have a lulling conversation, you can say, oh, that tanker came from Europe because it has this classification.
So can I ask you a question?
Yeah.
Okay, so of these 9 hazard classifications, assuming what I'm transporting, I am transporting safely. Can I take any of that anywhere at any time, or are there other rules that govern what I can transport, etc.?
It depends on the classification. So explosives, for example, you can only transport a certain amount, and actually it's very unlikely that you will see an explosive pictogram on the road because of their sensitive nature. So there might be a limit on the quantity. If it's something like radioactivity, for example, there'll be a limit on how much radioactive material you can carry. You can carry multiple types of goods, but again, so these, before these tankers go, they have to have a dangerous goods safety advisor advising on how they should be transported. So I don't know if that answers the question.
It does, thank you.
Okay. But yeah, again, it'll depend. It will have been classified beforehand. And essentially, in an ideal world, the driver should be able to hand paperwork to the fire service to say exactly what is on that tanker, what are the quantities, what are the hazards, what are the safety data sheets. But again, if you're transporting from France, for example, that might be in French. So it's probably not the time to try remember your GCSE French, your A-level French to translate it. So having this kind of universal number classification is quite helpful. So anyway, so that was just a bit about the classification side. So as I said, I'm going to talk about some incidents that we've been called out to under these 4 hazard classifications. I was going to do all of them, and then as I was realizing this was going on for a very long time. So they're in no particular order, and if anyone has other questions around the additional ones, then by all means ask, but I'll try cover it in that way. So first one, hazard class 3, flammable liquid. So the carriage of dangerous goods definition is saying it is a combustible liquid which can be easily ignited in air at ambient temperature. So that's what we're talking about with flammable liquids. So this was an incident we got a call about. You possibly saw it on the news as well, an M6 gin crash. So I don't really like gin, so I didn't feel too sad about it. But yes, there was a lot of comments, a lot of tweets came up about send someone out with straws and their tonic as well. So that was the resolution suggested by a lot of people. But essentially, 32,000 litres of gin potentially spilling onto the motorway. And is the M6, of course, so quite a busy one. So in terms of the fire service, when they turn up, what are their concerns? So again, casualties, so is the driver okay? But then risk to their own responders, how are they going to tactically respond? And the risk to the public. So turning up to a tanker like this was what they would see from a placard point of view. So they know straight away this is a flammable liquid. They have some advice on what to do in terms of whether they should use foam, whether they should use water spray, what they should wear. So they're, in this case, it's saying wear BA and fire kit. So they don't have to go all the way up to the Teletubby suit. That should be fine according to that placard. There is, of course, and this is something when you start getting into incidents, it's not just the fire service responding. You've got all the other agencies responding with their own concerns. So Environment Agency, start looking at what waterways are nearby. Can we let this go to drain, or where is that going to end up? Is it going to end up in the sewage treatment plant down the road and kill all the bacteria that, you know, treats our sewage? Is it going to kill all the fishies in the pond? So there's that kind of conversation as they're mobilizing will be had with the Environment Agency as well. And then of course the Highways Agency. So you know, we've all been stuck on traffic jams on the motorway. So you're talking the Highways Agency, the police are always trying to get the motorway open as quickly as possible. So we're trying to look at, well, actually, how safe is it? What is this substance? If cars are going to start traveling along at 70 miles an hour, is that motorway still okay to use? So there's all those kind of factors going on. And this is things that the fire service will be considering as well in terms of their response. So I can't talk about the fire service without talking about a fire triangle. So the kind of scientific concept I want to talk about with this one is flammability. So flammable limits and vapor pressure are quite good ones to think about. So this is the fire triangle. To have a fire, you need fuel, oxygen, and some energy. But it's not just simply okay to just have all those there. They need to be there in the right concentration, and they need to be mixed well. So if we're considering, I'll just go back to flammability limits. So flammability limits, like I said, we need to have the right mix of fuel and oxygen and air. So if something is too lean, so if you've got way more oxygen than fuel, it's not going to burn, even though it in itself might be flammable. So for example, this is gin. Why are we not worried that if we have a cigarette with our gin that we're suddenly going to burst into flames? And that again is to do with, you know, we're not in any sort of appreciable concentration. So there is, for flammable liquids, there is what's called a flammable range. So that is where you have the right amount or a good mix of fuel and air, such that if it had an ignition source introduced, you would have a burn. You would have it either flammable or explosive. So this is ethanol in this case, so because it's gin. So ethanol's range is 3.3% in volume to 19% in volume. So above 19%, there is too much fuel, so that won't burn until a bit more oxygen comes into play. And that is something that actually the gas safe companies are considering. If you ever have a natural gas leak, for example, you can actually get to a point where your whole room is full of the gas to the point where it's actually gone beyond the upper explosive limit for methane. So for flammability limits. So that is one thing the fire service will be considering. Do we have the right mix and enough fuel and air mixing together that should there be an ignition source, maybe something to do with the crash itself, could that potentially cause a fire? Oh, a random blank slide. Oh, this is my Robocop. It's kind of out of action here anyway. This was more a reference to people when they drop their cigarette into the petrol spill at the station, that you're not ever, your cigarette is not energetic enough to cause an explosion. I'm just gonna, that one came in at the wrong time, so I'll ignore that one.
Sarah?
Yes?
It's amazing. I've always thought that. So it's also shooting a gun bullet, and what's the other one? Dropping a Zippo lighter.
Yeah. So the issue with that one is, so you do have a fuel, but the problem with, for something to be on fire actually has to be in the vapor phase. So things are always evaporating, which is casually coming onto vapor pressure now. So things are evaporating over time. So dropping a cigarette into a pool of non-vaporized petrol, you're not going to have enough energy from that cigarette to actually get enough heat to vaporize it, to then mix with the oxygen, to then have a fire. So, you know, if you had a flamethrower, that might work. You might get enough heat that can vaporize enough of the liquid. And then when it mixes with the oxygen and gets the right flammability range, then it might ignite. So there's, unless you have a great big whopping cigarette and sustained heat, it's not going to get to that point. So I should have put that after this slide. But anyway, we all now know in a slightly haphazard way of explanation. So the other concept I want to talk about is vapor pressure. So I said about flammability limits. So do we have enough of a fuel-air mix? But actually, is there enough of it in the air in the first place? And that is down to the vapor pressure. So vapor pressure is a fundamentally measured process. So all liquids, like if you think about your glass of water or your beer, if that's what you have, if you manage to leave your beer for a couple of days, you would come back to an empty glass. So it's not evaporating straight away, but it is evaporating over time. And that's to do with the energy that's in the molecules. So in the liquid phase, you've got all these molecules bumping off each other. Some of them will gain enough energy to actually leave the liquid phase and head up into the atmosphere. If they're not in a closed system, like they are in this picture, they will actually just evaporate and disappear. So vapor pressure is essentially a measurement in a closed system at that gas liquid surface. So there will be a pressure. You'll have this equilibrium of molecules getting enough energy, bouncing off each other, leaving the liquid phase, losing some energy because of that cooling process and dropping back down. So at the interface between the gas and the liquid, you're going to have a pressure, and that is essentially what the vapor pressure is. And that is a fundamental property that you can look up. So the fire service will be interested when they figure out what substance it is, what is its tendency to evaporate? How likely is that pool that's on the motorway? How likely is there a flammable atmosphere, a vaporized version of that liquid up there, that should there be an ignition source that I'm actually going to go kaboom. This is just an example of some, so to give you an idea. So water has a vapor pressure, I'm going to work in kilopascals, of 2.34 kilopascals. So that is essentially, that is the pressure that would be at that surface. So if you think about your glass of water, like I said, how quickly is it evaporating? It's not going to disappear in the time it takes you to go to the toilet and come back. So that is typically its tendency to evaporate. Acetone, on the other hand, so whenever you open nail varnish remover, for example, you can smell the acetone. So it's actually evaporating. So in terms of a flammability risk, something like that with a higher vapor pressure, so there's more pressure pushing up, more tendency to evaporate, that is a bigger flammability risk. I put in there at 20 degrees as well. So these are measured at 20 degrees. And that is something, again, the fire service are bearing in mind. Is it a cold day? Is it a hot day? Because if we have a rare occasion where it's actually over 20 degrees in the UK, there will actually be more of that vapor in the atmosphere than you think. So that is essentially just covering the two concepts with that, flammability limits, vapor pressure. So back to the incident, in particular, the gin. So what is the greatest risk to the fire service? So for them, looking at it, flammability, they saw this flammability diamond. They've been told it can potentially react violently according to the emergency action code. So looking up the UN number, it says 3065 is an alcoholic beverage with more than 24% and no more than 70% alcohol by volume. So there's quite an appreciable amount of ethanol in that. Looking at the safety data sheet, the lower flammability limit is 3.3% volume and the upper flammability limit is 19%. So quite a narrow range, and they are outdoors. So it's unlikely that they're going to have, well, depending on the weather, I suppose, they will have an appreciable amount. Vapor pressure, hold on, I can't really read there, 44 millimeters of mercury, or I can only see the 6 parts, 60 something kilopascals. So quite a high tendency to evaporate. Toxicity is mentioned there as well, because that is another thing that someone might consider. Is there an inhalation risk? It's relatively high. This was again tested on mice, so it was 127 milligrams per liter over a 4-hour period. So they weren't massively worried about the toxicity from that point of view, and they are responding with breathing apparatus anyway. So the flammability risk was their biggest issue, and the fact that it will be evaporating. So they sprayed it with foam anyway to bring it down out of the atmosphere and keep it from evaporating. Environment Agency, from their point of view, it wasn't near waterways, so it wasn't really too much of a concern, but it is water miscible. So from their point of view, like I said, if that had gone into waterways, they're not going to retrieve it. So you'll be looking at, well, actually, do we need to, they have the Environment Agency have a facility where they can actually scoop the fish out of a river and move them somewhere else if they need to. So that could be something to consider if they had that issue. Yeah, it's quite interesting to see. But the Highways Agency then, so it's ethanol, it's not corrosive to the motorway surface. It is water miscible, like I said, so given that you could potentially wash it away, you should be able to actually open that road up to be safe. They didn't wash it away. They got a replacement tanker, which again, even that from an operational point of view, if you consider when you're stuck in a traffic jam on the motorway, getting a tanker to the source of the incident is quite an interesting feat as well. And then, of course, the police are just managing traffic diversions, facilitating response vehicles, entries, etc. Which is why having the hard shoulder is better to keep open rather than having it as a fourth lane. So that is flammable liquids. I don't know if there's any questions after that, or shall I move on? I think we're okay. Okay. So on to corrosivity. So corrosive substances. So these are those that can damage or destroy metal and cause irreversible damage to the skin. So the operative word here is irreversible. This is what makes something corrosive rather than just irritating. So burns, blistering, scars, etc. I'm not giving a specific example, but we do tend to get quite a few calls, unfortunately, to corrosive attacks. So they call them acid attacks, but actually, technically, it doesn't have to be an acid. So unfortunately, acids and alkalis are not controlled substances. So from that point of view, rather than walking around with a knife, for example, intending to stab someone, carrying a bottle of acid has kind of become a weapon of choice. So in terms of the fire service responding, what are the risks to them? So risks to responders. So inevitably, someone will have had a bottle of something chucked over them. So there may be a puddle on the ground. The public may have to walk through that as well. Ambulance, fast response needed. So one of the things that ambulance are always interested in, well, actually, are we dealing with a corrosive? Are we dealing with something else as well? So symptomology is quite important. In terms of a corrosive, you will generally know it's a corrosive because of the damage it has done to someone's skin, as opposed to having, I don't know, water thrown over them or lemon juice. So what makes something corrosive? You might have probably have seen the pH scale at some point. And this is essentially when we're talking about something being corrosive, we're talking about having a pH of less than or equal to 2 or greater than or equal to 12. So the lower end of the scale are the acidic things. So if you look on the picture there, battery acid, stomach acid. So battery acid is sulfuric acid. So that is right at the corrosive end, all the way up to 14, which is sodium hydroxide. So that's caustic soda, sometimes used in cleaners as well. So if you buy that thing to clean your oven, that is generally sodium hydroxide in a more dilute form, of course. So that is just the kind of scale we're dealing with. Within those two, we're talking about things that are potentially irritating, but not going to cause that irreversible damage. So like I said, if you have a bit of orange juice poured on you, it's not potentially going to do any damage. So what actually happens with corrosivity? What's the issue with these? So essentially, like I said, they can be acids or bases. So they are dissociating in water to give off H+ and OH- ions. So these are the things that are doing the damage, these ionic substances that are now reacting with your skin. So HX, so let's say hydrochloric acid, that would be HCl. When it's in water, it dissociates and it releases, you get the Cl-, but you get a lot of H+, which you make this hydronium ion. But essentially, the amount of dissociation determines whether it will be a weak or strong acid. So when we're talking about the amount of dissociation, obviously, hydrochloric acid is going to have millions of hydrochloric molecules in it. When you drop that into water, a certain amount of them are going to break up to make H+ and Cl-. Some substances don't do that. So as an example, so brick acid. So this is hydrochloric acid. When you drop hydrochloric acid into water, it almost completely breaks up or dissociates. So you've got loads of H+ ions available to float around and react with your skin. So that would be a strong acid. That is something that is going to cause you irreversible damage. What about your chips, on the other hand? Why are we quite happy to eat vinegar, acetic acid? And that is because when you drop acetic acid into water, almost all of it stays together. So most of it is still acetic acid. Only 1% of it will actually break up to release H+. So from that point of view, it is not going to have as many H+ to react and corrode your skin or cause irreversible damage. So yeah, happy to have vinegar on our chips, not so happy to have brick acid. So in terms, I'm just gonna have a drink. In terms of the greatest risk, so like I said, it's an irreversible injury. Sodium hydroxide seems to be one of the more popular ones. getting hit with a basic or an alkali substance is actually worse than getting hit with an acid, because once an acid hits your skin, it reacts and then it necroses the skin. So you end up with a kind of almost protective dead skin layer that stops it going further. Sodium hydroxide, on the other hand, like I said, used as a cleaner, tends to treat your skin or the tissues in your skin as like soap. So it just dissolves you into a waxy, soapy solid, and it will keep going without building up a layer. So quite a nasty substance. So for the police, their point of view, it's wash the skin of the casualty, try get that substance off. I have had conversations with the fire service saying, but wait a minute, if it dissociates in water, surely adding more water is causing more dissociation, which yes, there possibly is an element of that, but actually getting as much of the substance off your skin as possible. So I don't know if I think some memos went out around if you come across a corrosive attack victim, it's just get lots of water, try get that substance off them. For the fire service, if they can confirm the nature of the substance. So like I said, you could use hydrochloric acid, but if someone is really nasty, they could use hydrofluoric acid, which is an etchant as well. So fluoride is toxic. So you've also got a corrosive and a toxic nature. So confirm the nature of the substance, consider their own PPE as well. So not all your fire kit is to a point resistant to corrosives, but that is something to be considered. And then the local authority as well. So how do we clean this up? So like I said, inevitably, if someone has had something poured over them, some people usually have got some bottles of water and chucked it over. So you now have got a puddle sitting there. So do we actually neutralize that or dilute it? Remember, it's a log scale, so it actually takes quite a lot of water to make something neutral again. Yeah, okay, that's the end of that one. But yeah, so essentially, yeah, just talking about corrosives. If you're not on pH less than 2 or greater than 12, you're talking about potential irritants. And that is something we have had called about, people having solvents poured over them. So you might have some acetone, for example, poured over you, which evaporates and cools. So some people might think they've had a corrosive attack, but actually, if your skin is not damaged in the way that it does for corrosive, it's probably not a corrosive attack. Unfortunately, this still happens quite a lot. I think London said they probably have 5 or 6 a week corrosive attacks that they respond to. So we don't hear about them all, but it's still unfortunately quite a popular weapon of choice. Any questions on that one before I go on to oxidizers? Corrosives, happy enough for that one? I can't see the chat box, so I thought I'd be distracted, but okay. So
nothing in the chat, Sarah, so I assume silence is good.
Everyone's gone to sleep. So next one, oxidizing substances. So classification, these are a chemical that readily yields oxygen in reactions, thereby causing or enhancing combustion. So again, if we think about a fire triangle, you need fuel and you need oxygen. So oxidizing substances are giving oxygen to that reaction. If we talk about explosives, they will always have an oxidizer in them as well. So something that can intensify. And I think one of the more kind of biggest examples of an oxidizing agent recently was in Beirut, where the ammonium nitrate, which is an oxidizer, exploded. So in this case, I think the theory is that there were some fireworks burning nearby this ammonium nitrate, which was enough to give enough heat. If there's any sort of fuel source present, that will be enough to mix with this oxidizer. And it was just as ammonium nitrate decomposes, it starts to kind of give off NOx gases, which is the kind of brown smoke that you're looking at. So this was a very severe reaction of an oxidizer decomposing. And once you add confinement to something, it goes to detonation. So fireworks, for example, if we just burnt them not in their tube, they would just deflagrate. They would just give off a nice colored flame. Whereas when you start to confine things, which was in this case, I think it was 2,500 tons of ammonium nitrate, this went to detonation, unfortunately. So the incident we went to, so this is not the actual bath in the incident, and this one we get actually quite often. So essentially you've got a manky bath and you say, right, I'm really going to give this some welly. So you pull all the cleaning products that you have out of your bathroom and pour them all down the drain. In this case, it was Harpic, limescale remover and Domestos. So this older woman decided she would really give her bath some welly, poured it all down, and then started to feel a bit unwell with whatever gas ensued after. So what gas did ensue? And this is kind of the concern for the fire officers. What is the risk to the casualty and family? So when someone starts saying they've inhaled something, they're feeling unwell, there's obviously potentially toxic atmosphere there. So they need to consider that. Again, ambulance, they ideally would like to know what they're dealing with so they can offer the appropriate treatment. So,
Sarah,
yeah.
Got a question here on the chat from Roger. Roger's a chemist, and he says, why not put the actual chemical name on the label as well? Because he would find that really helpful.
For which labels? For the domestic product, commercial products.
The domestic products, I assume.
I suppose because I guess they've got other things in them. Also, the fire service will never tell you the actual chemical's name. I've had them say, "Oh yeah, I've got some methanol," and I say, "Is it methanol or methanol?" "Oh yeah, methanoic acid," and I'm like, oh, they're all very different things. So, I don't know if actually having the name would even make sure that it's the right that the information would get across. And I suppose Harpic sounds a little bit more buzzy than hydrochloric acid at less than 10%.
Or a chemical formula, I guess.
Yeah, well, they have. So if you look on that hydrochloric acid product name, they have identifiers there. So you've got the REACH number, which again is a classification system. The fire service used the CAS number, which is the Chemical Abstract Services numbers, and these are unique to that substance. So often, from a communication point of view, it's easier to list out some numbers rather than trying to tell you what they think they saw. So just to talk about the composition. So, and this is always, as we always say this to the fire service, you can only get out whatever elements you have in there. So you start looking at, well, what molecules and what elements are actually in these substances. So in the case of Harpic, the composition, you've got hydrochloric acid there in a concentration of less than 10%. In the bleach, sodium hypochlorite. So sodium hypochlorite is an oxidizing agent, with the operative concerns being an acid and a chlorine. And this is essentially what happened. And this happens quite often. Someone mixes their sodium hypochlorite with an acidic substance. As I said, oxidizing agents are giving oxygen. So they have it's given its oxygen essentially to the hydrochloric acid, making water and generating chlorine gas at the same time. So essentially, this lady had poured her two chemicals together and had made chlorine gas, which she subsequently inhaled. Quite a toxic gas. So the question that we always ask when we hear this incident is, how much hypochlorite was there? Because you can only generate as much chlorine as chlorine you had to start with. So in sodium hypochlorite solution, so in your household bleaches, you are typically looking at no more than 5% of the active ingredient of the hypochlorite. So if we think about how much chlorine, let's say she poured the whole bottle down, she's only going to have 5% of that 100 of that liter. So, I guess about 50 mil or something like that. So in terms of incident response, it is quite a toxic substance. So we would generally be looking at potentially ventilating. In terms of reactions for her, chlorine is quite an acute reaction. So it will burn your airways fairly quickly if you've got enough of it. So, we generally say if someone is not suffering or their symptoms have not worsened by now, they're probably at the worst they're going to get. The greatest risk for the fire service, inhalation of toxic gas. So I've put that, these are the EAGLES, so the acute exposure guideline levels, because again, we're not in a work situation, we're in an emergency situation. So quite toxic still at quite low levels. So for the fire service, from their point of view, is there other family in the house? Are they potentially going to have inhaled it? To go in and resolve the incident, what do the crews need to wear? Is breathing apparatus enough, given that it's corrosive as well as toxic? And this is kind of where knowing the quantities is important. If we're talking about a small bleach bottle in a bathroom, how much chlorine realistically is generated? Potentially she's inhaled it all, so there mightn't be any there. But so that's the kind of things they need to think about. So monitoring the atmosphere will be important to them. Ambulance assessing the extent of the injury quickly. And then, like I said, the fire service considering their PPE. We do get this call in relation to swimming pools as well. It's a classic. So you've got your disinfectant, which is often hypochlorite based as well, but you've also got your pH balancers. So we do have been called to incidents at leisure centres, swimming pools, where people have accidentally mixed those chemicals together and generated quite a lot more chlorine. So that would potentially be prompting an evacuation at that point. Okay, so any questions on the oxidizers? I kind of ran through that one a little bit, but I'm aware that I'm just waffling on and people are probably getting bored, but anyway. So final one I'll talk about is radioactive. Yeah.
So, sorry, there's one question from Bruce in the chat. Okay, Bruce says, from an A&E point of view, when someone attends, we search a database for the actual brand and product, e.g. Domestos, when figuring out the potential toxicity of the substance, presumably due to the other compounds.
Yeah. And I mean, this is always the tricky one, because the fire service, you know, they will get asked questions. We've had the police ask them questions to say, oh, I walked into that atmosphere. Do I need to send my officer to the doctor, or is it fine? And essentially, you can't really make that call. Everyone's physiology is different. So I will be very much deviating to what the medical services are saying. And they'll often, it could be a case that they have to take a blood sample to see, is there a toxicity level in that? But it's quite a tricky one. I guess from the fire services point of view, because they are responding in an emergency situation, they need to make the best guess they can at that time and save as much life and protect the public as much as they can. So yeah, they'll be working to that kind of level. Bruce
has just added that was to clarify the use of naming of the substance rather than the actual chemical itself.
Yeah. Oh, okay. Yes. Thank you for that. I shall bring that forth and educate the fire service about that if they ever ask me that question. Okay, so final one that I'm going to cover is radioactive substances. So this is class 7. Materials containing radionuclides. Oh, I've deleted some of it, where both the activity and the concentration essentially are exceeding a specified allowable limit. So radioactive substances are quite well regulated in the UK. So it is unlikely that you will come across a radioactive substance where there's no information about it and you're kind of walking in the dark. When we're talking about radiation, because depending on what field you're in, you know, you hear about electromagnetic radiation. You can hear about, I guess, essentially all types of radiation. And not all radiation is radioactive in the way that we think about a class 7. So the difference is whether it is non-ionizing or whether it is ionizing radiation. So ionizing radiation is the stuff that we're worried about. This is the thing that if it interacts with our DNA is potentially going to either alter our DNA in such a way that we have immediate effects, depending on how strong it is, or alter it over time such that it will actually change our DNA chemistry. So just to kind of give you an idea of scale, so when we're talking about ionizing radiation, the actual radioactive class 7 radioactive substances, we're up in that higher energy range. So we're talking about UV rays, gamma rays, X-rays. I've just put a little controversially put this 5G in there. So as you can see, 5G is nowhere near the ionizing side of radiation. We've got our microwaves as well. So I have been asked questions before. If I'm staring at my food cooking through the microwave, I'm actually irradiating myself. And the answer is no. It's a lower energy, longer wavelength. And if you ever look on the door of your microwave, there's a load of, it kind of looks like it's got a mesh on it with certain holes of a certain diameter. So essentially those holes are such that that wavelength of energy is not going to be able to pass through. So you can happily look at your dinner cooking in the microwave and you're not irradiating yourself. Just something to consider about when we're talking about radiation. So I don't know if anyone recognizes these badges. So if you've if you're building a house in a certain area, you might be asked, do you want to have a radiation survey? So essentially looking at radon gas, how much alpha radiation am I potentially being exposed to? When we talk about radiation, so as I said, it's well regulated. One of the things that in the regulated radiation sources will be activity. So how many becquerels? So if you're talking about radon, you usually get a becquerel value. So essentially activity is how many decays per second. So the analogy I like to give the fire service is, if I was throwing balls at you, how many balls am I throwing at you per second? And that is the activity. So something like Chernobyl, you're in terabecquerels. You're talking about a lot of balls being thrown at you per second. Radiation will decay over time. So carbon-14, if you think about carbon dating, that is essentially measuring radioactive carbon and how long it took it to decay. So when you buy a radiation source, it will have a specific date that it was measured at, because over time it will become less active as those unstable atoms start to stabilize. The amount of radiation absorbed. So if I kept throwing balls at you, you're going to get a bruise. So the size of the bruise is essentially what the radiation dose is. So works in 2 units usually. So grays and sieverts. Sieverts is specifically for energy absorbed by tissue, so for living tissue, whereas grays is can be non-living tissue as well. So medical sterilization facilities, for example, will measure things in grays. how many, you'll have an activity, which is often terabecquerels or gigabecquerels, very high energy source, and how much dose is it absorbing. And that is, unfortunately, the poor bacteria on your catheters, etc., are getting quite a big bruise. So it's typically, for the fire service, will be measured in microsieverts and millisieverts. If you want to think about a scale, if you think about in terms of a dose being life-changing, a microsievert is like me giving you a pound. Is that life-changing? Probably not. Go get a nice bar of chocolate. If I gave you millisieverts, 1,000 pounds, well, it might make you have a nicer month, but overall, long-term, it's not having a massive change to your life. So if you think about that in terms of doses, people get quite panicked about radiation, but actually millisieverts is not a very high level. So we typically in the UK get an average dose of about 2 to 3 millisieverts per year. So that's, like I said, an extra 2 or 3 grand in your life per year. It's not having a massive difference. So the incident we got called to, so this was a guy in his 70s decided to buy an old Spitfire dial, thought, yes, this will look really nice on my mantelpiece. So he started looking at, well, how do I clean these? So he started Googling how to clean a dial, and he started seeing all these warnings popping up about radium paint. So some of you may have heard about the radium girls. Essentially, radium is luminous, so it was often painted onto watches and painted onto dials so that the pilots could actually see the dials in the dark. However, radium, of course, is a radioactive substance, and these poor girls who were in the factories making the dials would lick their paintbrush every time to wet it, dip it in the radium, paint a bit on, lick it again. So unfortunately, after this, after World War II, was quite a lot of the radium girls with jaw deformities and massive tumors, etc., as a result of the radiation that they had been exposed to. So of course, as someone is reading up about how to clean their dial, I start to see all this and think, crap, what am I exposing myself to? So he called his doctor, who said, call the fire service. So sure enough, fire service turned out. So considering what are the concerns for them? So there is, when you're talking about radiation, there is risk of irradiation and there's a risk of contamination. So a good example of that is Litvinenko back in 2006, who unfortunately had a cup of polonium tea. So in his case, he was being irradiated. So he was getting the energy from these unstable nuclei, but he was unfortunately contaminated. And for him, very heavily contaminated. He'd actually ingested an alpha emitter. Unfortunately for him, he died 3 or 4 weeks later because he had this contamination inside him, continuing to hit him with this really high energy. But this is essentially what the fire service are concerned about. So looking at our radium dial, we have radium paint on there. So yes, if you were to take the cover off, you are now potentially having a contamination risk. This next slide, I didn't know if this was going to be a bit lowbrow, but this is generally how I explain it to the fire service, because when they go out to try tell their crews, there is a misnomer, because if people talk about alpha particles or beta particles, these are energy sources that come out, but because the fire service hear the word particle, they think something is going to land on me. So I generally like to explain it by this, radiation by dog poo. So if you think about a dog poo as your radiation source, so this is Litvinenko's cup of tea. The radiation or the poo is giving off a smell, and that is essentially the radiation, the irradiation risk. That's the energy coming out. So how can we potentially protect ourselves from this radiation? Well, we can spend less time there, so stop standing beside the poo and smelling it. We could put a bit of distance between us, move away from the poo so you can't smell it anymore. Or just put some shielding in place. So put a bucket over it so you can't smell it anymore. And that has essentially made that poo safe for the moment. So that is essentially reducing your irradiation risk. Now, what happens if you accidentally walk in the poo? Oh, I'm still smelling it. Oh, I'm still smelling it. So, and that is the risk with radiation. Have I contaminated myself, and am I continuing to smell that poo, continuing to be irradiated? And they're the two kind of risks. It's interesting to think, it's good to kind of get that clarification. So unfortunately for Litvinenko, because he was contaminated, he had essentially walked in the proverbial poo and was continuing to be irradiated. So unfortunately for him, a massive amount of radiation internally hitting all of his vital organs. And he had quite a horrific death where essentially the radiation stopped his gut lining being able to be regenerated. So the acid, his stomach acid ate him from the inside out. So quite a horrific way to go. But anyway, back to the dial. So Contamination risk, so it is radium paint. The paint does break down over time. So yes, if you decided to take the glass off the dial, there is a potential contamination risk. They could potentially walk in the poo, as it were. Other than that, there's an irradiation risk potentially. However, radiation is very predictable. So the fire service have radiation meters. So they measure a dose rate. Now, this isn't an absorbed dose, this is a dose rate. So if you think about your traveling along the motorway 60 miles an hour, it doesn't mean you're going 60 miles. It means if you drove for an hour, you would have 60 miles. So at the surface of the dial, when they put their meters, they were getting 1 millisievert per hour. So remember, we talked about a life-changing amount. That was £1,000 if you stayed there for an hour. So it's not a massive amount. Dose rate at the entry to the room, so that was 50 microsieverts. So again, that was at a distance from the source itself. So they simply said, yeah, if he left it on his mantelpiece and stayed close to it, it might affect his fertility slightly. Given that he was 70, he wasn't massively worried about his fertility at that time. So the end result was they just put it in the garage and left it there. And just to say about radiation, as I said, radiation is everywhere. People get a bit worried about it, the fire service in particular do, but actually we're constantly being exposed to radiation. The biggest of which is radon gas coming out of the ground. So like I said, if you are buying a house, you'll possibly be offered a radiation survey for a very expensive amount. But other sources, gamma rays from the ground, medical, so if you have any x-rays or scans, you're getting a higher than usual dose of radiation. So as I said, the UK average annual dose is about 2.6 millisieverts over a year. So not a massive amount. So in summary, I didn't know how to finish it, so I just put this random summary slide in. Again, these are photographs from incidents. Where can chemical incidents occur? These are all things that the fire service have gone out to. We've had motorway, transport issues, industrial sites. We're starting to see a bit of an increase in waste fires now. So you get people who decide to rent a warehouse for a certain amount of time, fill it up with rubbish, and then it accidentally goes on fire. And then, of course, they've rented it, so it doesn't really matter. So things like that. We do have some illicit incidents that we head to, and just things out of the ordinary. So ICE stands for individual chemical exposure, which is essentially chemical suicide usually. Malicious threats as well, so people sending white powders to people they don't like. And that is essentially all I have. I have other slides after that if people want to talk about other things, but that's essentially it. So if there's any questions, that's me done.
Oh, thank you, Sarah. Has anybody got any questions?
Stunned to silence.
No, Sarah, thank you very much. It's Martin. Yeah, are you seeing any instance? We're starting to get a lot of mobile lithium ion in batteries in electric vehicles and stuff. Has been anything happening around electric vehicles?
We haven't had so much electric vehicles. We have had battery fires at industrial storage facilities. So, I mean, I'm trying to think, there's nothing specifically around vehicles that comes to mind. The only issue they might have is if the alloys are made of magnesium, or if there's any kind of quite sensitive metals in the alloys. But generally, the ones we've had around batteries have been industrial storage facilities. And often it's been actually lithium ion batteries, so things that have fluoride in them, which becomes hydrofluoric acid in a fire. So that's kind of more what they've had. But I think it is something, green energy is definitely something we're going to start seeing more of. So we imagine that is probably going to start cropping up a bit more, incidents around batteries.
Tom?
Sarah, just before everybody disappears, thank you very much for presenting that tonight. I think this is the point where normally if we were doing this physically, everyone would give you a round of applause. So thank you ever so much.
Thank you, Sarah.
Hopefully it wasn't too long and waffly, but yeah, like I said, I could have gone on for longer, so I just thought
absolutely great. I think the format now is normally that if you're prepared to stick around for a Q&A session, if anybody's got any further questions, I'm going to stop recording the presentation now, so feel free to chat away. If not, thank you very much for attending tonight. I've just posted details in the chat of our next meeting, which is next month. And
Stephen.
also, just to let you know, our colleagues over at Kirkby Cyber are running an event tomorrow evening. The details of that also are in the chat if anybody's interested.